Hi, I'm Robert Padalano, and thanks for attending this Science in Action session. I'll be discussing different biological marker molecules, or biomarkers, and their applications to archaeological research. I know we've already had a few other talks covering various biomarkers, so I won't go too in depth on the biogeochemical background of these techniques, but I will give you an overview of some of the projects I'm involved with as a postdoctoral fellow at the Max Planck Institute for the Science of Human History, and how we are using different organic proxies to answer questions on the human past.
You already heard a few fantastic talks on the multiple biomarkers being used in archaeology. Even though these are lab-intensive analyses, over the last 10 or 15 years, these biomarkers really have changed the way we do archaeological fieldwork, mostly in how we sample soils and sediments in close association with archaeological or paleontological assemblages. I'm going to mostly focus on biomarkers that allow us to reconstruct past climate and environmental conditions, such as those used as proxies for past plant ecology and hydroclimate. My research interests are in environmental change and human origins, and we know that climate variability and hominin evolution are inextricably linked. Yet hypotheses examining the impact of large-scale climate shifts on hominin landscape ecology are often constrained by low-resolution proxy data coming from off-site lake and ocean cores and temporal offsets between the paleoenvironmental and archaeological records. Biomarkers allow us to address these issues because we can sample from directly on-site and at higher resolution, especially compared to pedogenic or tooth enamel carbonates. The biomarkers that will be the focus of this talk are plant wax lipids. On the outer surface of leaves is a layer of wax that protects the plant from such things as harmful UV radiation, insect and fungal attack, excessive water loss, and wind abrasion. This wax is made up of a number of organic compounds, some of which can be extremely long-lived and are chemically inert and resistant to biodegradation in sediments following deposition and initial diagenesis. This includes fatty acids here on top and N-alkanes down at the bottom, which are ideal proxies if we are targeting compounds for carbon and hydrogen isotope analysis to reconstruct plant ecology and hydroclimate. Here at Max Planck, we are leading and contributing to multiple projects around the world that are involving plant wax biomarkers in their archaeological and paleoanthropological research. We've analyzed samples from as old as 2 million years to those collected from modern environments in the past few months. I'll highlight a few of these projects today. But first, let's look at how we use plant waxes and their isotope ratios to interpret paleoproxies. During photosynthesis, plants take in CO2 from the atmosphere, and that CO2 is made up of both carbon-12 and carbon-13, as well as carbon-14. Certain plants discriminate against the different carbon isotopes, and as you see here, C3 plants prefer the lighter carbon-12 and therefore have lighter or more negative isotope ratios compared to C4 plants. This results in distinct bulk and compound-specific isotope values between C3 and C4 species. As you see here, because of those distinct values, we can interpret past plant landscape changes such as between C3 or C4 dominated environments. Plant waxes have also been used to look at the expansion of C4 grasses across eastern Africa over the last 10 million years, and have helped to show that some environmental hypotheses, like the savanna hypothesis, cannot explain human evolutionary events like the emergence of bipedalism or early tool use. Now, in areas where only C3 plants grow, interpreting environmental and climatic changes using only carbon isotopes can be a bit difficult, but we will get into that in a little bit. Plants obviously need water for photosynthesis and growth, and their hydrogen isotope ratios is largely determined by source water hydrogen values, as well as total amount of rainfall, temperature, rainout processes as clouds move across continents, and degree of evaporation. Now, these factors and differences in plant life forms can make interpreting ancient hydroclimate complicated. But in tropical Africa, where much of our human evolution research is done, hydrogen isotope values are largely determined by amount of rainfall, with more negative isotope values coming during periods of increased precipitation. And this climate variability between wet and dry phases had a significant influence on hominin habitat types, as it largely determined the plant landscape, with more rainfall allowing for an increase in the relative abundance of C3 trees and shrubs. Okay, let's now take a look at some of the projects where we have applied biomarkers to paleoanthropological and archaeological studies. Here at Ewos Altapa, a site in the western part of Oldapai Gorge where the earliest Oldowan in the gorge was found, plant wax and alkanes were used in combination with other proxies like phytoliths, tooth enamel isotopes, and sedimentology to reconstruct the ecological conditions in an area where a lot of hominin activity occurred. And what was significant about this multi-proxy approach is that we showed that early Homo, likely Homo habilis, occupied heterogeneous, unstable environments, and that cultural remains associated with habitats from post-volcanic disturbances. This is actually an early example of adaptation to major geomorphic and ecological transformations. The analkanes themselves show changes between open and closed ecological conditions. In this example, a few different samples from throughout the Ewos Altapa stratigraphic column are showing changes between C4 dominated, as in sample 2, C3 dominated, as in sample 3, and mixed ecology, as in sample 1. And when combined with the other proxies, we were able to show that regardless of habitat type, hominins were exploiting the landscape and quickly colonizing the area following volcanic eruptions. Early evidence of this ability to respond to rapid changes in the environment suggests that the fundamental aspects of human adaptability had actually emerged by the time of our genus's African origin. If we jump ahead in time a bit and look at Oldapai's earliest evidence of the Acheulean, around 1.7 million years ago, analkanes show that hominin activity occurred in a relatively closed, well-wooded environment. When the landscape started opening, however, the number of artifacts decreased, suggesting that the location no longer acted as an ecological magnet of sorts. Interestingly, hand axes from the site don't seem to be used for butchery, but rather for digging and processing plant foods like tubers. And who knows, perhaps these plant foods disappeared as the plant landscape opened and hominins moved on to a more productive area in the gorge. Let's get out of Oldapai and head down south to the Kingdom of Lesotho. We just did an isotope study looking at modern topsoil samples from 3 altitudinal transects in the eastern part of the country, ranging from 1,800 to 3,000 meters above sea level. We wanted to see how changes in temperature, as associated with elevation change, impacted the distribution of C3 and C4 grasses, and how this can be used to interpret Pleistocene temperature changes, and how that may have influenced the appearance of the Middle Stone Age in Lesotho. We compared both bulk and N-alkane carbon isotopes, as there was no modern ecological baseline for these proxies from the region, even though they have been used in archaeological settings. There are a few major things we discovered in this study. As you see in this example, samples from south-facing, cooler slopes show a much better correlation between isotope values and temperature, with higher altitude/cooler temperature samples having lower or more negative carbon isotope values. But on the north-facing slope, this relationship is not as clear, likely because the warmer temperatures are allowing C4 plants to grow at higher altitudes. Actually, what we see is quite alarming, as we notice C4 plants growing at altitudes nearly 400 meters higher than previously observed in 2015. We also see some differences between the bulk and N-alkane carbon isotopes, which we believe is related to microhabitat variability and the bulk carbon recording non-plant sources. However, this shows the importance and necessity of taking a multi-proxy approach to reconstructing past environments in archaeological settings. Let's move to an area crucial for the dispersals of people from Africa and the Middle East into Asia, but vastly understudied. At the Pebda site in Iran, we use biomarkers to look at the ecological and hydroclimate history of a Middle Stone Age occupation in the southern Zagros Mountains. Many of our samples came from marine isotope stage 3, about 45,000 years ago or so, and show a much wetter and woodier environment, especially compared to today. Looking here, we actually don't see much change in our hydrogen and carbon isotope records until we get to level 2, which is Holocene and dated to only about 5,000 years ago, and obviously not a focus on a Middle Stone Age study. But in the Pleistocene levels 3 to 6, we see a C3 dominated environment with pretty consistent rainfall amounts. This was likely a great area to be to withstand more extreme climate fluctuations due to glaciation, as it was fairly consistent through time. If we compare the paleo record to modern rainfall in the region, we see that it was much, much wetter in the past. Here on the right is monthly precipitation from the southern Zagros today, and you can see that the average hydrogen isotope values of rainfall is only about minus 17 per mil, with the most negative values coming in the colder, wetter winter months. This is quite a bit higher compared to the minus 100 or so per mil average of the paleo record, and shows how much different the region was during the Pleistocene. Let's actually get out of the Pleistocene and head to northwestern China during the Han Dynasty. You're probably more familiar with the brick and mortar Great Wall of the Qing Dynasty, but the earliest Great Wall was actually made of rammed earth and plant matter fascines like you see here. We sampled grasses from the Han-era Great Wall segments and beacon towers to see if we could identify localized environmental signatures for when the wall was constructed. We looked at plant wax distributions and bulk carbon and nitrogen isotopes. In the N-alkane distributions, we see much greater variability in the chain lengths of Great Wall grasses compared to modern correlates, suggesting that there was much greater diversity in plant ecology in the past. It seems that desertification in the region has removed much of the previous biodiversity over the last 2,000 years. As for the carbon isotopes, there is quite a difference in samples from east and west of our study transect. Western cluster samples have higher carbon values, likely due to the warmer temperatures and higher degree of evaporation in the west compared to samples from the east. As you compare this to the ancient Great Wall grasses, which are much more homogeneous, not only do we see higher values in samples from today, suggesting a greater degree of evaporation, but also differential rates of environmental change across the study region, with the West suffering more from environmental stress and climate changes. We have a few other projects currently underway. We are now studying the plant waxes from the Lesotho archaeological assemblages to look into human highland adaptations to temperature changes, the presence, or perhaps lack thereof, of a Pleistocene savanna corridor in Southeast Asia, and the degree to which Pangaya Saidi in Kenya was able to withstand global climate changes during periods of glaciation and possibly acted as a refugia for human groups over the last 80,000 years or so. I hope these projects show you how plant wax biomarkers can be used in numerous archaeological projects. They have great potential for answering questions on human-environmental interactions and can be applied in many settings and timeframes. If you have any questions, don't hesitate to contact me. I'd also just like to thank all of the organizers for the Human Origins in Action workshop, as I know it's been a ton of work behind the scenes. I hope you enjoy the rest of the sessions, and please stay tuned for some amazing upcoming biomarker and archaeology research.